Hello everyone, Professor Dustin here, and in this video I'm going to give you a real quick introduction to partial derivatives. So this video is going to be in two parts. The first part is just going to be like, why do we need partial derivatives, and how do you use them? And that's really, as physicists, the extent that we need, right? A lot of mathematical ideas are very in-depth and very complicated, but often we just need to know how do we use them to achieve the modeling of the real world that we want. So that's the first part of the video. The second part is just going to be like checking, because mathematicians are careful people and we want to make sure that they are doing things correctly and that we understand them. It's just checking to make sure we understand partial derivatives in the same way that we understand regular derivatives. So the second part of the video is kind of optional. You can check it out if you'd like. It's good to know this stuff all makes sense, but the first part of the video is really like, how do we use this stuff? So first let's motivate this thing I'm calling a partial derivative. So here's the equation of a traveling wave, which is in the video that you just watched from the Khan Academy. So the traveling wave is the displacement of something, usually it's like a string, but it could also be an electric field or a water wave, whatever. The displacement in the y direction, so up and down, has an amplitude. It's a cosine function. It could be a sine function too, but it's a function of both x and t. And so that's because as you travel along the wave, the amplitude of the wave changes. That's a wave. But also the wave is traveling, meaning it's moving forwards in time. The wave is propagating in a particular direction. So if you wait a certain time period, the wave is going to pass you at some rate. And so because it's a function of both the position and the time, that's essentially the problem we have when taking derivatives of these things. The functional form here is kx plus or minus omega t plus phi. Remember, in the video, they actually used a slightly different notation, so let me just identify that other notation real quick. So the other notation is k is the wave number, but if you want to relate that to the wavelength, which might be something you're more intuitively understanding, that's 2 pi over lambda, where lambda is the wavelength. Omega is the angular frequency, but you can also relate that to the regular period by saying 2 pi over the period time, so the period t. So this is either written this way or written this way. In either case, it's a function of two variables. And that's really the critical problem, because if it's a function of one variable, we know how to take that derivative. But if I go up to you and I say, take an x derivative of this thing, you're like, okay, I think I know how to do that, because like that's a constant, k is a constant, there's my variable. That's a constant, phi is a constant, but what do I do with time? Time is a variable thing. It is a changing thing. So if I take a derivative with respect to it, with respect to x, what do I do with time? I don't know what derivative to take of that. That's how partial derivatives come in. And actually the great thing is that it's super simple. A partial derivative just says, assume all the other variables are constant. So it's got a different notation, so here's the other notation. So the notation is very similar to a regular derivative, right? A regular derivative would have a Roman d and a Roman d on the bottom, right? dy dx. This is a slightly curly d to indicate that we're doing a partial thing. But partial means take the derivative of y with respect to x, but keep everything else constant. So if there's another variable in there, just assume that variable is constant. In this case, because t is there, assume that t is constant. Sometimes people will be a little bit more careful and they'll actually write like this with a little t down there. That means they're saying very explicitly to you, assume t is constant. I usually won't do that. I'll usually just do partial y, partial x is how you say it. So let's just do this one real quick just to see what it looks like when you try to take a partial derivative. So that's the derivative. That's evaluating, putting y into there and evaluating, saying, I am now going to evaluate the derivative. Well, I'm going to hit the derivative here, and the same thing is going to happen. That's got a constant, it's going to get pulled out. That cosine is going to become a minus sine, and then I'm going to be faced with doing a chain rule here. But let me first get that first derivative part done. So that's the derivative of the cosine function. Now I need to do a chain rule. So over here, I'll have something, partial with respect to x of the entire inside of the cosine, kx plus or minus omega t plus phi. And now I'm faced with actually taking the derivative of this thing, keeping in mind what partial means, which is everything else is constant. So when I hit here, I just get a k, because x is the variable, so I just get k. Everything else is constant, so I can just ignore t, assume it's a constant. The derivative of, with respect to x, of omega t plus phi is just 0. So this whole thing is just k. So it almost couldn't be easier, in fact. I mean, just the fact that partial derivatives actually work this way just is the best way they could possibly work. You just take the derivative and you assume everything else is constant, not a variable, and then you're back in the situation of doing regular derivatives. So that's the first part of this video. This is what we need to actually do physics. Second part of this video, which I'm going to tell you what it is before you decide to watch it, is just like, are we sure this really works with the definition of the derivative from calculus? So the way that I'm going to prove that it actually does is I'm going to prove that the partial derivative is commutative in the same way that the regular derivative is commutative. So let me just remind you what that means. For a regular derivative, that would mean something like the following. So in other words, it doesn't matter what order when you take second derivatives, if you take first the t derivative and then the x derivative, or if you do the other way around, first the x derivative and then the t derivative. So what I'm going to prove is that, okay, so we should all know this is true for total derivatives. What I'm going to prove is that it's also true for partial derivatives. And that's going to be the second part of the video. So stop now if you're done, but also if you want to see that, it's a pretty cute little example of the real definition of derivatives from your Calculus 1 class. So hang on to that, or I'll check you later and see you in class.